Yeah, I just click on that record button. It's once it starts, I will start the class. Yeah. So good evening, all. So the last class we have discussed about the sequencing static methods and also the maximum delay constraints. Okay. So what do you mean by maximum delay constraints? Hello, guys. Hello. Hello.
Yes, ma'am.
What do you mean by maximum delay constraint? Hello.
Setup violation, ma'am.
Yeah, if the combinational logic delay is too great, receiving element will miss its setup time and sample the wrong value. So this is called as maximum delay failure or a or a setup time failure. Okay, if the combination logic delay is too great, the receiving element will miss its setup time and sample the wrong value. This is called as setup time failure or a maximum delay failure. So this can be avoided by increasing the clock period or by what is the other method? You can increase the clock period or by redesigning the combinational logic to be faster. Are you getting it? Okay, so this can be avoided by redesigning the combinational logic to be faster or by increasing the clock period. Okay, so now and all the three methods we have discussed. Okay, so with respect to the flip-flop, with respect to the two-phase transparent based latch system, and with respect to the pulsed latch system. Okay, in today's class we are going to discuss about the minimum delay constraints and clock skew and time borrowing. Okay, so 1 minute. Is it appeared?
No, ma'am.
No, ma'am.
Not yet.
Okay. I have given a present now option, but I don't know what happened.
No,
Now it is coming.
no, ma'am.
Hello. No.
ಶೇರ್ ಸ್ಕ್ರೀನ್ ಕೊಟ್ಟು ನೋಡಿ ಮ್ಯಾಮ್ ಒಂದ್ಸತಿ.
Ma'am, or else leave the meeting.
Yeah, share screen only I have given yesterday.
Ma'am, leave the meeting again and join, ma'am.
What?
Probably then you will be able.
Yeah, 1 minute. Could you able to see now?
Yes, ma'am. Yes, ma'am.
Hello?
Yes, ma'am.
Okay. Sorry, I don't know what happened. That was option only. It was not giving actually. Okay. Okay. So what do you mean by minimum delay constraints? Okay. Suppose if you consider if the whole time is too large, okay, whole time is large and the contamination delay is small. Contamination delay is nothing but your TCD, okay, or TCCQ, clock to queue contamination delay, okay. So or D to Q contamination delay. So if the hold time is large and the contamination delay is small, the data can incorrectly propagate through two successive elements on one clock edge. Okay, so one clock edge, because all this is edge triggered flip flops, we are using it, right? So this data is incorrectly, it is going to propagate through two consecutive the two successive elements on one clock edge. Okay, so what it happens if it the two successive elements on one clock edge, if it comes, what happens? It is going to corrupt the state of the system. It is going to corrupt the state of the system. So this is called as a race condition or a hold time failure or a minimum delay failure. This is called as race condition because race condition, you know, in the JK flip flop, you learned the concept like to overcome that race around condition, we are going for a master slave flip flop. That concept, you know. So here also, since the two successive elements, so the data can incorrectly propagate through two successive elements in one clock edge, and it is corrupting the state of the system, and it is called as a race condition or a hold time failure or a minimum delay failure. How it can be fixed? How it can be avoided? So it can be fixed by redesigning the logic, combinational logic, not by slowing the clock. Okay, in case of a maximum delay constraints, we can avoid that setup time failure by increasing the clock period or by redesigning the combination logic. But in case of your minimum delay constraints, we cannot slow down the clock. Only option is left out for us is we can only redesign the combinational logic. Okay, so this is an example of the flip-flop based minimum delay constraints. So look at the circuit diagram. So the statement is common like whatever we discussed in the last class. Okay, so this figure is going to show the minimum delay constraints on a path from one flip-flop to the next, because F1 will be the first flip-flop, next flip-flop will be the F2, one flip-flop to the next. Okay, and here also we have assumed that it is ideal clocks, there is no skew. Okay, so the path is always begins at the rising edge of the clock, and it is going to trigger the F1, and the data may begins to change at a Q1. So the data is going to begins to change at Q1 only after clock to Q contamination delay. The data is begins to change at Q1 only after clock to Q contamination delay. You can see this timing diagram. Here it is written as TCCQ. Okay, and then it is appearing at D2. Okay, then it is appearing at D2 after the another logic contamination delay. You can see the diagram. So after TCCQ, I have written here as TCD. So it is going to appear at D2 only after the contamination delay, that is TCD, that is based on your that delay, it is coming from your combinational logic circuitry. Okay, and at D2 after another logic contamination delay, that's what I said, but it must not reach D2 until the whole time after the clock edge. So it will not immediately, it will not appear at D2, because it will appear at D2 only after the whole time, that is a T hold after the clock edge. Okay, so once it appear at D2, again on the next rising edge of the clock, so the F2 flip-flop will be triggered. Okay, then that data is going to appear at Q2 and so on. So what is the equation we can write, like how we have written for the maximum delay constraints? What is the equation we can write? Guys, what is the equation we can write? So what is a TCD? TCD is your combinational logic. That's what I said. Here the option is only one. We have to redesign the combinational logic. Whereas in case of your maximum delay constraint, there are two options. Either you can increase the clock period or by redesigning the combinational logic. That's why we have wrote the two equations there. One is the TC should be less than or equal to, TC should be greater or equal to what we have written, TPD plus TPCQ plus T setup. Okay, or the TPD should be less than or equal to TC minus sequencing over it. That's what we have discussed in the last class. But here we are not going to write the two equations. We are writing only one equation because only we are redesigning the combinational logic. So what is the equation it is expected over here, guys? Hello. See, at least you should answer the question whatever I ask. Otherwise, I'll not come to know whether your people are listening or not. Hello.
Yes, ma'am. 1 minute.
Yeah, next time onwards. Huh?
Yes, ma'am.
Suraj? Yeah, what is the equation to redesign the combinational logic? What is the constraint equation you're writing it here? Hello? See, it should be an interactive class here. Yeah. So somebody wrote, Saurabh has wrote. So Saurabh, it is TCD should not be less than, it should be greater than or equal to. TCD should be greater than or equal to T hold minus TCCQ. Okay. So you can see here, the equation is your contamination delay TCD should be greater than or equal to T hold minus TCCQ. Okay. So that is clock to Q contamination delay. Are you getting it? Your logic contamination delay should be greater than or equal to the hold time minus clock to Q contamination delay. If you see the timing diagram, you'll get to know the idea. Because TCD will be the combinational logic. So this TCD should be greater than or equal to this hold time minus your clock to Q contamination delay. Okay. So now, any doubt in this? Hello?
No doubt.
At least
No.
say yes or no.
No doubt, ma'am.
Okay.
No
So
doubt,
shall we
ma'am.
move on to the, with respect to your two-phase transparent based latch system?
Yes, ma'am.
Now look at this diagram. This is with respect to your two-phase transparent based latch system. So there are two latch clocks, that is phi 1 and phi 2. Okay. So this figure shows a minimum delay constraints on a path from one latches. So the path is going to begins with the data passing through L1. So when the data is passing through L1, when only on the rising edge of phi 1, only if the latch is opaque or if the latch is transparent, then only that particular data is appearing at Q1. Okay. It must not reach L2. It must not reach L2 until the hold time after the previous falling edge of your phi 2. Very, very important sentence. Okay. It must not reach L2 until a hold time after a previous falling edge of phi 2. Previous falling edge of phi 2. That's what you can see that timing diagram over here. The phi 1 and phi 2. So this we are calling it as a T non-overlap. Okay. So whenever your phi 2 is on, phi 1 will be off. And for some duration, both should be off. That is nothing but T non-overlap. Okay. So it should not be. And again, the phi 1 is going to rise. Okay. So that's what I'm telling you. It must not reach L2 until a hold time after a previous falling edge of phi 2. Because L2 should have become safely opaque before L1 become transparent. Okay, so L1 should become safely opaque before your L2 should have become safely opaque before your L1 become transparent. So these edges are separated by T non-overlap. So here one more delay gets added. So if you look at this timing diagram here, not only the TCD, TCCQ, T hold, there's one more delay it gets added, that is nothing but T non-overlap. So as the edges are separated by T non-overlap, the minimum logic contamination delay through each phase of the logic will be what? You have, because there are two latch clocks. There are two latches. So there are two latch clocks, that is phi 1 and phi 2. So I can write it as, what is the equation? TCD1 comma TCD2 should be greater than or equal to T hold minus your TCCQ, that is clock to queue contamination delay, minus T non-overlap. So that will become added because edges are separated by T non-overlap. If you are not if the T non-overlap is not there, then what happens? So we'll not come to know whether which latch is transparent or not. So if the same time both the latches are transparent, it is corrupting the state of the system. So the data can catch up with another data, will not come to know, or the data, whatever the data, it is coming in a form of a pipelined fashion. So that data will get mixed up. We will not come to know which data. So to avoid that, we are using a T non-overlap. The edges are separated by T non-overlap. So if you see the equation 8, so TCD1 comma TCD2 should be greater than or equal to T hold minus TCCQ minus T non-overlap. Any doubt?
No, no.
No, ma'am.
Hello, any doubt? Okay. Now, we'll explain still further about this. What is this T non-overlap? Okay. Suppose, if you make this T non-overlap sufficiently large, what happens? If you make your T non-overlap is sufficiently large, what happens?
Then hold time increases.
Yeah, hold time failure can be avoided,
Yes,
right? Hold time failure can be avoided if you make this T non-overlap is sufficiently large. So it preventing the data with catching up with another. Okay. But however, this generating and distributing this T non-overlap clocks is very challenging, especially at high speeds. So it is very, very difficult. So what may be the delay of this? How much should be kept? Everything. It is a challenging for the designers. Okay. That too, if you are dealing with very high speeds. So therefore, most of your commercial transparent based latch system uses a clock and its complement. That is, if phi 1 is on, phi 2 will be off. Then if phi 2 is on, and phi 1 will be off. Okay. But what happens in this case? That is T non-overlap. If it is equal to 0, then the contamination delay constraint is same between the latches and flip-flops. Yes or no? Suppose if you're taking the clock and its complement, okay, if your T non-overlap will be equal to 0, exactly it will be the same, then what happens? Your contamination delay constraint is the same between the latches and the flip-flops. So this, what happens? So this is not actually, the contamination delay constraints is applies to each phase of the logic, because in case of your two-phase transparent based latch system, we are using two half cycles. Okay. In the first cycle, we are using first half cycle, there is a combination logic circuitry, and the second half cycle also there is a combination logic circuitry. So the contamination delay constraint is applied to each phase of the logic for a latch based system, but for the entire cycle of logic for the flip-flop based system. Would you able to make the difference between the two-phase transparent based latch system and the flip-flop based method. Here, the contamination delay constraints is going to apply for each phase of the logic. That's what you are going to get TCD1 and TCD2. Whereas in case of your flip-flop based system, it is going to use an entire cycle of logic. That's why you are going to get only TCD over there. Okay. So what I want to convey the message is the latch seem to require twice the overall logic contamination delay as compared to the flip-flops. It is obvious because I said no, the two combinational logic circuitry are there and it uses two latch clocks. There are two phases. So TCD1 and TCD2, obviously it takes twice the overall logic contamination delay as compared to your flip-flop based system, because flip-flop based system uses only one cycle of the combination logic. So that is only TCD. Are you getting it? Hello?
Yes, ma'am.
Yeah. So now we will move on to the
Yes,
pulsed based latch system. So look at this circuit diagram, pulsed based latch system. So the minimum delay constraints on a path from one pulsed latch to the next. Okay. So obviously the data is going to depart on the rising edge of the pulse. Okay. You can see here in the timing diagram, the data is going to depart at the rising edge of the pulse, but must hold, very, very important, must hold until after the falling edge of the pulse. You can see here, you can see the whole timing waveform. Okay, so falling edge you observe, that is the rising edge, it is only TCCQ for the Q1, and in between I have written here TPW, that is a pulse width. And if you observe the pulse, the falling edge, you can see the T hold time. Okay, so the data is depart on the rising edge of the pulse, but must hold until after the falling edge of the pulse. So data should hold until the falling edge of the pulse. So the pulse width is going to effectively increase the hold time of the pulse flash as compared to the flip-flop. Okay, so because it should hold the data for that particular duration, so it is going to, the pulsed based latch system, it is going to increase the hold time of your pulsed latch as compared to the flip-flop. Okay, so what is the equation you can expect over here?
Plus TPW.
What is the equation you can expect over here? Plus TPW, exactly correct. It is plus TPW. Your TCD should be greater than or equal to T hold minus TCCQ plus TPW, because it is going to increase the hold time of the system. Okay, so I will show the equation over here. Okay, so TCD should be greater than or equal to T hold minus TCCQ plus TPW. Okay, so this is with respect to your minimum delay constraints. Okay, any doubt in the minimum delay constraints? Any doubt?
No, ma'am.
Hello, are you there, guys? Okay.
No doubt.
So now I'm moving on to the concept called time borrowing. So till now I've assumed it as ideal clock skew, and there is no time borrowing. Okay, so look at this circuit diagram. Okay. Okay. So look at this circuit diagram. So this is, I'm going to explain the concept of time borrowing. As the name itself indicates, so we can borrow the time. Suppose if one of the clock cycle, it takes only the less time. So the second block, if it takes the second cycle data, it is huge, it takes more time. So you can just take the borrow from the previous clock cycle, like that. Okay, so as the name itself indicates, it is a time borrowing. Okay, so let us again, I'll talk about with respect to the flip-flop, but in the diagram, whatever I've shown here, the flip-flop based method is not shown. So because why I am telling you, there is a disadvantage in time borrowing in case of a flip-flop based method. So the diagram A and B shows with respect to the two-phase transparent based latch system and the pulsed based latch system. Okay, so suppose in case of a flip-flop, what happens? The data is going to depart at the first flip-flop on the rising edge of the clock, right? Must set up at the second flip-flop before the next rising edge of the clock. If the data arrives late, the circuit produces the wrong results. If the data arrives too early, it is blocked until the clock edge and remaining time goes unused. Are you getting it? What is the disadvantage of a flip-flop based method in case of time borrowing? Okay, so we know that the data is going to depart on the first rising edge of the clock, and then it is going to appear at D2 on the second rising edge of the clock. Suppose if the data arrives too too late, then the circuit may produce us the wrong value. Suppose if the data arrives too early, it is going to lock. Okay, so the data will be locked, okay, until the next rising edge of the clock, and the remaining time will goes unused. Are you getting it? Yes or no?
Yes, ma'am.
Okay, so that's what the time borrowing is not possible in case of your flip-flop based method. Is that clear? Time borrowing is not possible in case of your flip-flop based method.
Yes, ma'am.
Yes, ma'am.
So now we'll discuss about the two-phase transparent based latch system, current latches. So we know that the data can depart in the first latch on the rising edge of the clock, okay, but does not have to set up until the falling edge of the clock on the receiving latch. So only we are going to do the setup on the falling edge of the clock, that we know when we have discussed for the maximum delay constraints. Okay, so if one half cycle or a stage of a pipeline has too much of logic, that's what you can see in this dashed vertical lines. If one half cycle or a stage of a pipeline has too much of logic, here there is a too much of logic. Are you getting it? Okay, in the first block has a too much of logic, it can borrow a time into the next half cycle. I'm also stress the word called pipelining. If the second block, again, it takes a too much of logic, it can borrow the time for the third clock. If the fourth block, again, it takes a too much of logic, it can take the fifth clock, and so on. Are you getting it? If one half cycle or a stage of a pipeline has a too much of logic, it can borrow a time into the next half cycle or a stage. Okay, are you getting it?
Yes, ma'am.
So like that you can keep on borrowing. So next, so phi 2 is going to ask phi 3, phi 3 is going to ask phi 4, phi 4 is going to ask phi 5. Okay, phi 1 and phi 2, it comes under one clock cycle. Phi 3 and phi 4, it is coming under the next clock cycle. Are you getting it?
Yes,
So
ma'am.
you can keep on ask the time from the next half cycle. Are you getting it?
Yes, ma'am.
Hello?
Yes, ma'am.
Yeah, but what is the disadvantage?
Ma'am,
What is the disadvantage?
hello? Hello?
What is the disadvantage here? Advantage is that you can keep on, you can borrow the time from the next
Hello,
half
ma'am.
cycle, right?
Hello?
Yeah, tell me.
Yeah, ma'am, if all the
Hello, tell me.
data is sampled at different times, then it will be a problem, no, ma'am. Like no synchronization will be there.
At the end of the half cycle, we have to see. At the end of the half cycle, we have to see. Then we will come to know whether we have to increase the clock period or what is the problem like that. So that is a disadvantage in case of a pipeline based system. Are you getting it? So this time borrowing can accumulate across multiple cycles. Okay. But are you getting it? The time borrowing, it can take a multiple cycles. Okay, but if you see the second method, what is advantage in the second method? If you're looking at this diagram, what you can say?
Some sort of feedback.
Hello? Yeah, some sort of feedback is there, but have you observed the clock cycle over here? Have you observed the clock cycle? It takes only one clock cycle. You can borrow the time only to your neighboring house. Not to the second house or a third house or a fourth house. Are you getting it? So if you see this figure B, it shows a single cycle self bypass loop. We are calling it as a single cycle self bypass loop, in which the time borrowing, it is going to occur across half cycles only. So, but the entire path must fit in one clock cycle. Whatever you want to do, the entire path should consume only one clock cycle. So that's what, if the first half cycle, it takes too much of combination logic, you can borrow the time only with the next half cycle or the neighboring house. You cannot ask for the second cycle, second clock cycle. Are you getting it? So the entire path must fit in only one clock cycle. Hello, are you getting it, this concept?
Yes, ma'am, little bit.
Hello, guys. Little bit you understood.
Yes, ma'am.
Ashwita.
Yes, ma'am.
Ashwita, Rahul.
Hello.
Yeah. Nivedita, are you people are understanding
Yes,
this
ma'am.
concept? Are you people are
Yes,
understanding this concept? So if you go for a pipeline based method, you can keep on borrowing the time from the neighboring house. But if you go for a second logic, you can borrow the time only with the neighboring house or the next half
Yes, ma'am.
cycle. But the entire data path should fit in only one clock cycle.
Okay, ma'am.
Okay,
Okay.
ma'am.
Okay. So next. Okay. So this is the concept of the maximum amount of time borrowing. What is the maximum amount of time borrowing? Which is the circuit diagram I'm just talking about with respect to your timing diagram, with respect to your two-phase transparent based latch system, right? There are two latches are there, phi 1 and phi 2 are there. So what is the maximum amount of time borrowing you can do it? That is what we are discussing now. Okay. So in case of a two-phase latch based system, can borrow, how much it can borrow? It can borrow TC by 2 minus TP dq. You can see the timing diagram here. It's TP dq. TP dq means clock to Q propagation delay. Clock to Q propagation delay. You can see here, this is maximum amount of time borrowing means propagation delay is coming into the picture. Minimum amount of time borrowing means contamination delay is coming into the picture. So that's what, if you see in this timing diagram, so you can see here T setup is coming into the picture and TPDQ, that means clock to Q propagation delay is coming into the picture. So I'm talking about the maximum amount of time borrowing. Maximum amount means propagation delay. Minimum amount means contamination delay. Okay. So
Yes,
if
ma'am.
the two-phase latch-based system can borrow Okay, it is TC by 2 minus TPDQ, and it is because the data does not have to set up until the falling edge of the receiving latch clock. You can see here the setup time is based on your falling edge of the receiving latch clock. Receiving latch clock will be L2. Receiving latch clock will be L2. So one phase can borrow up to a half cycle of time from the next. So one what I was saying, one phase can borrow up to half a cycle of time from the next. So what is the equation I can write for this particular circuit diagram is T borrow should be less than or equal to TC by 2 minus T setup plus T non-overlap. That is equation 10. So why it is TC by 2? Because one half cycle. It should be TC means full cycle. So TC by 2 is one half cycle. And also I said that the data does not have to set up until the falling edge of the receiving latch clock. That's why it is TC by 2 minus T setup plus T non-overlap. So T non-overlap will be there. Okay. Are you getting it? So yeah, with respect to the pulse latch can also be viewed as a transparent latches because we are giving a narrow pulse and only one pulse will be used during the entire cycle. Suppose if the pulse is wider than the setup time, there are two cases, right? If the pulse is narrow, what happens? Pulse is wider, what happens? That we have discussed with respect to your maximum delay constraints, right? So if a pulse is wider than the setup time, the pulse latches are also capable of small amount of time borrowing from one cycle to the next. So if the pulse should be wide, if the pulse is wider, then it can borrow the time. If the pulse is narrow, then it is not possible. Borrowing is not possible. Are you getting it? So two-phase transparent based latch system, we can easily borrow the time from next half cycle or from the next to next half cycle. That is a pipeline based method. But flip-flop based method, time borrowing is not possible. Pulsed latch system, time borrowing is possible. If it is a narrow pulse, it is not possible. If it is a wide pulse, then it is also a capable of small amount of time borrowing from one cycle to the next. So what we can write the equation is T borrow should be less than or equal to TPW minus T setup. T borrow should be less than or equal to TPW minus T setup. Okay. So what is the benefit for the designer for the time borrowing? What is the benefit? Hello guys. Hello. Yeah, are you there?
Yes, ma'am.
Hello.
Yes, ma'am.
Yeah, what is the benefit for the designer for time borrowing? If you do time borrowing,
Hold time increases.
whole time increases. No. What is the benefit means? What is the advantage? See, the time borrowing has two benefits for the system designer. See, first of all, there are two types of time borrowing. What is that is intentional time borrowing. Okay. And the next method is opportunistic time borrowing. So there are two types of time borrowing: intentional time borrowing and opportunistic time borrowing. Okay. Then what do you mean by intentional time borrowing? As the name itself indicates, in which a designer can more easily balance the logic between half cycle and the pipeline stages. Because when you go for a pipeline stages, so the designer, he has to redesign the combination logic for the next to next half cycle. Like that, he has to do it. Okay, so that is called, okay, if I design the third half cycle with a less combinational delay logic, then I can increase the delay in the first in the first cycle of the combinational logic. So like that, he'll be thinking it and he'll be designing the circuit according to that. That is called as intentional time borrowing. Intentional time borrowing in which the designer can more easily balance the logic between the half cycle and the pipeline stages. Okay. So are you getting it? So then what do you mean by the opportunistic time borrowing?
Whenever you get
Ma'am, is
time,
it when it's needed?
What is it? What is that? Because opportunistic time borrowing is that, so the designer has to be very careful and he has to equalizes the delay in each stage at a design time. So the delay is going to differ from one stage to the another in the fabricated chip because of the process and environment timing model used by the CAD system. So it is very difficult actually. Opportunistic time borrowing is very, very difficult because he should be a more experienced person to design to go for a opportunistic time borrowing. Okay. So the concept is left out for recap is the clock skew that I'll be doing in tomorrow's class. And again, I'll be starting the new chapter in the syllabus. Anyway, all these concepts are required to start the static analysis. Otherwise, you'll not understand. Are you able to understand?
your voice is breaking, ma'am.
Hello, guys.
Ma'am, your voice is breaking.
Voice is breaking.
Now it's fine.
Hello.
Yes, ma'am.
No, it's
Yes,
fine.
ma'am.
Okay.
Now it's
Okay.
audible.
So, yeah. Hello. Before that, you not understood?
Ma'am,
Hello.
you were telling something about syllabus that I
Hello.
couldn't hear itself.
Hello, ma'am.
Okay. So yeah. So the next clock skew concept is left out. That I will be doing in tomorrow's class. Plus, I'll be starting with the new introduction to your as per the syllabus, that is static timing analysis chapter. But all these concepts are required. Otherwise, you will not understand anything.
Okay.
Because it's more or like it's a theory type only. Okay, and problems are there. It is it is direct type calculation problem, like delay calculation, setup time calculation, hold time calculation, like that. The problems are also very simple, and we can ask only the problems for 3 to 4 marks, not more than that. So the problems are also simple, and also more or like you have to write the timing diagram and explain the theory. Write the timing diagram, explain the theory. So like that, it will be there. Okay, so and also you should analyze it, how it is possible, and all those analysis is very, very important. Even if I tell 2 times repetition also, you should go to your head and analyze it, how it is possible. Oh, these delays are coming. So that's what initially I gave introduction. If you use a latch, what all the delays are coming into the picture. If you use a flip-flop, what are the delays coming into the picture. If you use only the combination logic, you get only 2 delays, TPD and TCD. If you use a flip-flop, you get what are all the delays? Setup time, hold time, TCCQ, TPD, TCCQ, TPDQ. Okay, if you use a latch, all the delays are coming into the picture, right?
Yes, ma'am.
D to Q contamination delay, D to Q propagation delay, clock to Q contamination delay, clock to Q propagation delay, contamination delay, propagation delay. So all the delays, when you use a latch, it is coming into the picture. Okay, so I'll take the attendance now. Only 4 minutes is left out. Okay, so I don't know what is the problem. Again, I closed, leave the meeting again. So it was shared actually. Okay, so I will take the attendance now. Please turn on your video and show your face to me. Okay, and say present. Okay. Yeah, USN number 1.
One is not there, ma'am.
1.
One is not there. He's left the college.
1 is not there.
Abhishek has left the
Oh,
college.
1 is only left. 2. Okay, 2. Okay. 3.
Present, ma'am.
There is no. Okay, fine. 3. 4.
Present, ma'am.
Yeah. 5.
Present, ma'am.
6.
Present, ma'am.
6.
Yes, ma'am.
Okay.
Present.
7. Who is 7? 7. Next 8. 8. Who is 8?
8 present, ma'am.
Okay. 9. Who is 7? 7 is Nikhileshwar.
Yes, ma'am.
Huh?
Yes, ma'am.
Then he's not answering. The 7 is present, no?
His webcam is open, ma'am. His
Okay.
web-
Okay. So 8 is over. 9. 9. 9 absent. 10. 10 absent. 11.
Present, ma'am. Present, ma'am.
11 absent. 12.
11
Huh?
present, ma'am.
Okay. 12. You can turn off your video. 12. Okay. 13.
Present, ma'am. Present, ma'am.
Wait. Okay, 13. 14.
Present, ma'am. Present, ma'am.
Okay. 15.
Present, ma'am.
Okay. 16. Okay. 17. Once attendance is over, you can leave the meeting. 17. 17. Who is 17? Past 18. 17 is absent, right? 18. 18. 19. 19. Absent. 20.
19 present, ma'am.
Yes, ma'am.
19 present.
Yeah.
Okay, Kiran. Yeah, 20.
Yes, present, ma'am.
19 present. 20.
Present, ma'am.
20 Niva.
30.
Ah?
Present, ma'am.
Maulab, your USN is what?
20.
Okay, done. Next 21.
Present, ma'am.
21 video.
Present, ma'am.
Virle ansette video. Video, turn on your video.
Yes, ma'am, I have turned on.
Turn on your video.
I have turned on my
Yeah.
video.
Your USN is 21.
Yes,
Okay. Shesha Sai, your USN is 21.
yes, ma'am.
Okay, you can leave the meeting. 22. 22. Okay, 23.
Present, ma'am.
Nivedita, video.
Yes, ma'am. Present, ma'am.
Video.
I've switched it on, ma'am.
Okay. 24. Nivedita, okay. 24. Who is 24? Pampapati is 24. Voice is not audible.
Unmute.
Okay, 24 is Pampapati.
Yes, ma'am. Present.
Okay, 25.
Yes, ma'am. Present, ma'am.
25.
Yes, ma'am. Present, ma'am.
Who is present? 25 is Prasanna Kumar.
Prajwal team.
Yes, ma'am. Present, ma'am.
Prajwal.
Who is
Prajwal team.
25? Prajwal video.
Camera is not opening.
Video ತೋರಿಸಿ ಅಂತಾರೆ HOD ಮ್ಯಾಮ್. 26.
Yes, ma'am. Present.
Okay.
Yes, ma'am.
27.
Present, ma'am.
Okay. 28.
Yes, ma'am.
29.
Yes, ma'am.
29. Video.
On, ma'am.
Okay. 30. You can leave the meeting. 30.
Present, ma'am.
31. Fine. Saurabh, ನೋಡ್ದೆ. 31. You can leave the meeting, Saurabh. 31. 31. Okay, 32. Suraj is 31. Huh? Not audible.
32.
31. Who is 31 then?
Sunil, ma'am.
ಎಲ್ಲಿ ಸುನಿಲ್ ಬಂದಿಲ್ವಾ? ಸರಿ. 32 is ಸೂರಜ್. ಓಕೆ. 33.
Yes, ma'am.
ಯಾರು 33?
Govardhan.
ಓಕೆ ಸರಿ. 34. 34. ಯಾರಪ್ಪ 34?
Ma'am, Vinayak absent.
34 ಅವರಾ? ನೆಕ್ಸ್ಟ್ 35. ಯತೀಶಾ?
ಹೌದು ಮ್ಯಾಮ್.
36 ಯೋಗಾನಂದ?
ಹೌದು ಮ್ಯಾಮ್.
ಯೋಗಾನಂದ್ ವಿಡಿಯೋ ಇಲ್ಲಪ್ಪ, ನೋಡೋಣ ನಿಮ್ಗಳ ಮುಖ ನೋಡೋಣ, ಖುಷಿ ಆಗತ್ತೆ. ಸೊ 9, 10, 17, 18, 31 and 34 are absent.
Yes, ma'am.
Okay. 9, 10, 17, 18, 31 and 34 are absent.
Yes, ma'am.
Okay. Thank you all.
Thank you, ma'am.
Thank you, ma'am. Thank you.
Okay.